Okay, so today's lecture, we're going to continue on our material regarding stoichiometry. And so the general form of a stoichiometry problem, we consider a chemical equation with the following form, where we have uppercase letters are the molecules and the lowercase letters are our stoichiometric coefficients, which are our molar ratio. So if we have A plus B, our reactants, yields C plus D, and then we have our stoichiometric coefficients A, B, C, and D. The stoichiometry allows for the conversion between the mass of one molecule to the mass of any other molecule, whether it's a reactant or a product. So if we start with the grams of A, we can then convert to moles of A using the molar mass. Then we can convert between moles of A to moles of B using the molar ratio, which is given to us by our chemical equation. And then we can again use the molar mass to be able to convert between moles of B into the grams of B. So these are just using different forms of our conversion factors to be able to convert from one quantity into another using stoichiometry. So let's consider a problem where we are converting between mass of one material into the mass of another material. So aqueous solutions of sodium hypochlorite, NaOCl, best known as household bleach, are prepared by the reaction of sodium hydroxide and chlorine gas. And so we have our chemical equation that has been provided for us here. So our first step that we would like to do here is just to make sure that everything is balanced in our chemical equation. So we can see that in both cases we have so we start off with our sodium hydroxide, and so there are two sodiums on the reactant side, and we have two sodiums on the product side. We have two oxygens, because remember that 2 coefficient gets transferred to every different atom within that molecule. So we have 2 oxygens over on the left. We have 1 oxygen plus 1 oxygen is 2 on the right. We have 2 hydrogens on the left, and we have 2 hydrogens on the right. We have 2 chlorines on the left, and we have 2 chlorines on the right. So we've confirmed here that we have a balanced chemical equation. So how many grams of NaOH are needed to react with 25 grams of Cl2? Okay, to work through this problem, we first need to take a look at what we're trying to do here. So we have our mass of Cl2 that we're given. Then we need to convert that to moles of Cl2. Need to convert that guy now into moles of NaOH. And then we can convert that to the mass of NaOH. Okay, so we can determine the molar masses now of Cl2 and our molar mass of NaOH. So if we look up on the periodic table for the molar mass of Cl2 is going to be equal to 2 times the molecular or the molar mass of chlorine, which is 35.453 grams per mole. So if we plug that into the calculator, we get an answer of 70.906 grams per mole for Cl2. Now if we take a look at the molar mass for NaOH, that's going to be equal to our molar mass of sodium, 22.9898 grams per mole, plus the molar mass for oxygen, which is 15.9994, plus the molar mass for hydrogen, which is 1.0079. And that gives us a value here of 39.9971 grams per mole, which is our molar mass for sodium hydroxide. Okay, so now we need to convert our mass of Cl2 to moles of Cl2 to moles of NaOH, then to mass of NaOH. So we always start with the measured quantity first. So our measured quantity that was in the problem was 25.0 grams of Cl2 gas to start with. So our first step here is to go from mass, which is going to be grams of Cl2, into moles of Cl2. So to do this, we need to use our conversion factor, which will be our molar mass of Cl2, which we already calculated above. And so since this is a conversion factor quantity, it's actually equal to 1. So it's not actually changing the value at all. So we're going to convert from grams to moles. So we have 70.906 grams of Cl2 gives us 1 mole of Cl2. Now we want to convert our moles of Cl2 to moles of NaOH. And to do that, we refer back to the chemical equation that was on the previous slide, and that showed us that we had a 2-to-1 molar ratio of NaOH to Cl2. So we convert now. There's 1 mole of Cl2 for every 2 moles of NaOH. And again, that molar ratio came to us from the chemical equation. Next, we need to now convert from moles of NaOH into our mass of NaOH in grams. So again, we want to cancel out our moles of NaOH, so that has to go on the bottom of our stoichiometry here. So for every mole of NaOH, it is 39.9971 grams of NaOH. Okay, so we can see grams of Cl cancel, moles of Cl cancel, moles of NaOH cancel, and we're left with grams of NaOH, which is what we're looking to solve for. So we have our final answer here of 28.2 grams of NaOH. Okay, and we have our 3 significant figures, which was determined not by any of these conversion factors, but this was determined from our initial measured quantity, the 25.0 grams, which had 3 sig figs to start with. Okay, so that was a mass-to-mass conversion. Okay, so now we will take a look at a mass-to-mass conversion that has some additional dimensional analysis to it as well. So the combustion of hydrocarbons releases carbon dioxide into the atmosphere. Some chemical reactions can remove or sequester carbon dioxide from the atmosphere into a pool for long-term storage. Below is a sequester reaction where carbon dioxide combines with a naturally occurring mineral. Okay, so we have this sequestering reaction that occurs down here. Again, you want to go through to make sure that that chemical equation is first balanced before you move on. Okay, so you can take a moment to take a look at that, and I'll show you that the equation is balanced. So we asked the question, what mass in kilograms of magnesium silicate, which is this Mg2SiO4, is needed to sequester 1 pentagram, so that is a 10 to the 15 grams, of carbon dioxide? Okay, so it's the same sort of idea, except for this has an additional dimensional analysis in that we have a unit conversion that we have to take care of. All right, so let's work through this one. So it's the same sort of idea. We're going to start off with a mass of CO2. We're going to convert that into moles of CO2, which is going to then convert to moles of Mg2SiO4. And then we're going to convert that into our mass of the Mg2SiO4. Okay, and then we have a couple unit conversions in there. Okay, so we start off using our measured value, which in this problem was given to us as 1.00 times 10 to the 15 grams of CO2. And again, we would start with our measured value over 1. We're going to use our molar mass of CO2 to convert our grams into moles. So I'll let you be able to determine that molar mass of CO2 on your own. So we can say that the moles of CO2 are equal to 44.0099 grams of CO2. So now we've converted our mass now into moles of CO2. Based on our molar ratio that was given to us in the chemical equation, we can see now that we have for every 2 moles of CO2, there is 1 mole of the Mg2SiO4. And then we use our molar mass to be able to convert our number of moles into number of grams. For every 1 mole of the Mg2SiO4, we have 140.6936 grams of Mg2SiO4. All right, the same sort of experimental setup or equation setup that we used last time. So this final answer here gives us a result of 1.60 times 10 to the 15 grams of Mg2SiO4. Okay? Let's move on to the next. Okay. Sorry, there's one more step here that I did not give to you guys. And so that is our final conversion. So the idea here is that this has an additional dimensional analysis to it. So we solve for that answer in grams, but the problem is asking for the mass in kilograms. Okay, so let's go back to our whiteboard for just a moment. And so we can see here that our final answer that we calculated was 1.60 times 10 to the 15 grams of Mg2SiO4. And we need to now convert that into kilograms. So there are, for every kilogram, there is 1,000 grams. Okay? So that will give us our final answer now is 1.60 times 10 to the 12 kilograms of Mg2SiO4. Okay, so you need to make sure before you submit the answer to the problem that you double check and take a look to make sure that you are in total understanding of what the question is asking. Okay, the yield of chemical reactions. So rarely do all the reactants convert to form products. There are sometimes side reactions, there's loss of sample due to experimental mishaps, any number of ways that you can lead to a loss of some of your sample. So there are a couple terms that we need to discuss when we are figuring out how much of a product is actually produced. So the one term is called experimental yield, which is the amount of product that is actually formed in a reaction. So that's the amount that if you ran a chemical reaction, you would actually go to the balance and be able to measure out what the experimental yield was. The theoretical yield is the amount of product that is theoretically possible to be formed. And so this is the amount based on calculation of how much that you could possibly form. So because of the aforementioned reasons before, there's a likelihood that you're not going to actually produce the amount of yield of a reaction as you experimentally expect you would based on the theoretical yield. And so we have this quantity called the percent yield, which is equal to the experimental yield over the theoretical yield times 100%. And so what that does is that tells you how efficient was your reaction. The closer your percent yield is to 100%, that would mean that the 100% percent yield would mean that your experimental yield, the amount that you actually produce, would be equal to the theoretical yield, which is the amount that you expect. A very low percent yield would indicate that you lost a lot of your sample or lost a lot of your product due to any manner of reason. If you have a percent yield that's over 100%, that would mean that you would have an impure product. Because remember, we can't actually create matter. That would mean that maybe your solution has some water in it, or there's something else that you haven't totally purified your sample before you measured it. So percent yield is a very valuable sort of quantity that we can calculate. Very useful. Okay, so ethyl alcohol is prepared industrially by the reaction of ethylene, which is C2H4, and water. What is the percent yield of the reaction of 4.6 grams of ethylene to produce 4.7 grams of ethyl alcohol? Okay, so we have our percent yield, we have our actual yield, which gives us our 4.7 grams. That's the product that we actually produced, so that we can actually see what we can measure it out and see that's how much we produce. And the 4.6 grams, that's how much of the starting material that we had. So based on that starting material of what we began the reaction with, we can actually figure out what our theoretical yield is, and then compare that then to the actual experimental yield. So let's work through that. So again, as a sort of a shortcut here, I'm going to assume that you are all capable of determining the formula weight for both C2H4 and C2H6O. So the molecular or the molar mass that we have for the C2H4 is going to be equal to 28.05396 grams per mole. And the molar mass that we're going to use for the C2H6O is going to be equal to 46.06924 grams per mole. Okay, so we're going to determine our theoretical yield now. So based on the amount of starting material that we had, so we said that we started off with 4.6 grams of the C2H4. And since that was a measured quantity, we take that and put it over 1. We're going to use our conversion factor to be able to convert that mass into number of moles. So since we're working with C2H4, we're going to use this molar mass up here. And say if we put the molar mass of 28.05396 grams of C2H4 is equal to 1 mole of C2H4. So now we have a value that is in moles of C2H4. We need to now convert that into number of moles of our product. And it will, based on the chemical equation, we saw it was a 1-to-1 ratio. So 1 mole of C2H4 gives us 1 mole of our product, C2H6O. And now to determine our theoretical yield, we would want to convert these moles of C2H6O into grams, using again our molar mass as a conversion factor. So for every 1 mole of C2H6O, you have 46.06924 grams of C2H6O. You can see all of our units are canceling out, and we get a final answer for our theoretical yield of 7.6 grams of C2H6O that we expect to find. So our problem asked us to be able to solve for the percent yield. So our equation for percent yield is equal to our experimental yield over the theoretical. The theoretical yield and then times 100%. So the theoretical yield is the calculated amount that we expect to produce based on our starting material. So that's calculated here as 7.6 grams. The experimental yield, that is the amount that we actually produce. So that was given to us in the problem. So in this case, we have our percent yield is equal to 4.7 grams of C2H6O, which was given to us in the problem, over 7.6 grams of C2H6O, which we would just determine, times 100%. And so our final answer here with 2/6 would be 62% is our percent yield for this reaction. Okay, so that is a percent yield problem. So limiting reagents. So reactions are rarely carried out using the exact molar ratios defined by a balanced chemical equation. So typically there's one reagent that's limiting and the other reagents are in excess. Okay? And so the limiting reagent is the reactant that is present in the limiting amount. The extent to which a chemical reaction takes place depends on this amount of the limiting reactant. Whereas the excess reactant is any of the other reactants that are still present after determination of a limiting reactant. Okay, so to describe limiting reactants and excess reactants, I typically use the analogy of making peanut butter and jelly sandwiches. So imagine that you have a big old jar of Jif peanut butter. And so imagine with that big jar of peanut butter, you have enough peanut butter to probably make 50 different sandwiches. And you have a jar of jelly, and so you probably have enough jelly to make 25 sandwiches. Your limiting reactant for how many peanut butter and jelly sandwiches you make is usually always your bread. If you only have 6 slices of bread and you need 2 slices of bread per peanut butter and jelly sandwich, obviously with 6 slices of bread, you can only make 3 sandwiches. So the bread in that case would be the limiting reactant because you've used up all of that bread. Whereas the peanut butter and the jelly would be considered excess reactants because you have some left over and you haven't totally used it up. So the same idea would occur for a chemical equation. So for example, consider the burning of a hydrocarbon to produce carbon dioxide and water. Okay, so if we're thinking of, we'll just do methane because it's the easiest. We have methane gas combusting with oxygen gas to form CO2 and water. So this combustion of a hydrocarbon, so you can think of this as the fueling of your car. Okay, so burning of that octane in your car is the same sort of idea. The oxygen obviously is in excess because that is in our atmosphere. We don't have a limitation of oxygen, but we have a limited amount of our actual hydrocarbon, the methane in this case, or the gasoline in our car. So that hydrocarbon itself would be the limiting reagent. This O2 gas that's in the atmosphere would be your excess reagent. Okay? And so the amount of your limiting reagent is what determines how much of the product that you can form. Okay, so let's consider the industrial synthesis of ethylene glycol. So at high temperature, ethylene oxide reacts with water to form ethylene glycol, which is an automobile antifreeze and the starting material in the preparation of polyester polymers. So we have this chemical reaction here that defines that equation. So water is so cheap and abundant that it is used in the excess when compared to this ethylene oxide. So in this case, this ethylene oxide here is going to be our limiting reagent. The water here is going to be our excess. So which is the limiting and which is the excess? I just defined it for you. Let's actually visualize this in terms of the molecules themselves. So this is the same reaction. It's just sort of trying to identify them for you. Okay, so for the sake of this video here, because it's a little tough to see, I'll circle our water molecules. So that guy's a water, that's a water, that's a water, that's a water, and that's a water. Okay, so there are 3 ethylene oxides and there are 5 water molecules. Okay, based on our chemical equation here, it says we have a 1:1:1 ratio, which means that this reaction can only occur to the extent of the limiting reagent. So since there are only 3 of these ethylene oxides, only 3 of these waters can react with them to produce our product here. And so what we're left with are 2 waters that remain here at the end. So the idea that one of the reactants is still present at the end indicates that it is an excess reagent. So therefore, it's pretty clear to see, ethylene oxide, since it's not present as a product, is our limiting reagent, and water is our excess reagent. Okay, so let's consider the same reaction. If 3 moles of ethylene oxide react with 5 moles of water, which reactant is limiting and which reactant is present in excess? So the same sort of idea. So the last case, that was visualizing on our microscopic sort of visualization. Here we're jumping up to that macroscopic, where we're talking about the number of moles, something that's more tangible that we can hold. Since it's a 1-to-1 to 1-to-1 ratio, we have our 3 moles here of our ethylene oxide. We have 5 moles of water. Okay, obviously we're going to run out of our ethylene oxide before we use up all of our water. So we would then produce 3 moles of our product here. That would identify our ethylene oxide as our limiting reagent. And we have our water here as our excess reagent. Okay, now let's consider the same reaction and let's flip it. If there's 5 moles now of ethylene oxide, and there's 3 moles of water, and we're still a 1-to-1 to 1 ratio here, obviously the water now is going to be used up now before the ethylene oxide. So we can again only form 3 moles of our product, and now the water is our limiting reagent, and our ethylene oxide now is our excess reagent. So whichever one is used up first is going to be your limiting reagent. Now let's consider if we have 5 moles of ethylene oxide reacting with 5 moles of water. Which is going to be our limiting reagent and which is going to be excess? So in this case, they're both the limiting reagent because neither of them is in excess. There's exactly the amount of ethylene oxide as there needs to be to react with the water, and there's just enough water to react with the ethylene oxide. So we're producing 5 moles of our product. We have exactly the amount that we need. Okay, so what's the method that we need for mathematically determining the limiting reagent and experimental yield from our mass of reactants? So we already sort of started on this with our discussion of stoichiometry at the beginning. So we have our balanced chemical equation with that sort of generic form of A plus B equals C plus D, with our lowercase letters being our coefficients. If we're given the number of grams of our starting material A and our number of grams of our starting material B, we can then convert into number of moles of the same thing. So whether we convert from number of grams of A to moles of B, or we start with number of grams of B and go to moles of A, we just need to put them into number of moles of the same thing. So for that case, you could even change it to number of moles of one of the products. But the idea is if you convert them both stoichiometrically into the number of moles of the same thing, you can compare the two and say which one can produce more product and which one can produce less. The starting material that can produce less product is going to be your limiting reagent, and the starting material that can produce more product is going to be your excess reagent. Okay, so we see our grams of A converting into moles of A, and then converting into moles of B. Whereas our grams of B can go straight into moles of B. Now these are both moles of the same thing. So we can directly compare the two to see which one expects to produce more. Okay, and then that can then give you what your limiting and your excess reagents are. All right, so let's work through an example. So, lithium oxide is used aboard the space shuttle to remove water from the air supply according to the following equation. Li2O plus H2O gives us 2 LiOH. So if 80 grams of water are to be removed and 65 grams of lithium oxide are available, which reactant is limited? How many grams of excess reactant remain, and how many grams of lithium hydroxide are produced? Okay, and then provided here for you are all of the formula weights, or the molecular mass of all of these, or the molar mass of all of these compounds. Okay, so, these are the molar masses of each element, and then you can use those to determine the molecular weights of all of the different compounds. All right, so this sort of problem is a very, very common problem that I can ask during tests and quizzes. So you should become very, very comfortable with working through one of these problems. Okay, so if you're given the amount of both starting material, identify which is excess, which is limiting, how much of the excess is left, and how much of the product that you're going to form. Okay, so let's work through this problem. So the first step is going to be determining the molar mass of all the different compounds involved. And so I will assume again that you can do that. So for Li2O, it's going to have a molecular weight of 29.8774 grams per mole. For H2O, we have a value of 18.01528 grams per mole. And for LiOH, we have a molecular weight of 23.94634 grams per mole. Okay, so now we want to see we need to determine which one of these are going to be our limiting reagent. So first, let's start with water. So we know that we have 80 grams of water to start with. That's our measured value, we put that over 1. And then we're going to convert this now into number of moles of water. So we know that our molar mass for water states that 18.01528 grams of water gives us 1 mole of water. Grams cancel, we have our answer in moles of water. So there are 4.44 moles of H2O available. Okay, so that's how many moles of water that we start with. To determine the limiting and the excess reagent, we need to now convert the mass of the other starting material, the lithium oxide, into the number of moles of water that it needs to react with in order to determine which one is going to be limiting. So we know that we start off with 65.0 grams of lithium oxide, again over 1 since it's a starting material. We use our molar mass here to convert into moles of lithium oxide. 8,774 grams of lithium oxide. Now we want to convert that moles of lithium oxide into moles of H2O. And we go back to our chemical equation and we see that it's a 1-to-1 ratio. So for every 1 mole of lithium oxide, we have 1 mole of H2O. So we can see our grams cancel with grams, moles of lithium oxide go with moles of lithium oxide, and we have our final answer, which is in moles of H2O. So this answer shows that 2.18 moles of H2O are needed. So 2.18 moles of H2O are needed in order to react with this 65 grams of lithium oxide. So here, since we've now converted these both into moles of the same thing, we can now compare and say which one is going to be our limiting reagent and which one's going to be our excess. So since there is less moles of water for this lithium oxide, That means that this guy has the capability of producing less product. So because of that, this lithium oxide is considered our since that has a lower number of moles, that means that it is there's a possibility to produce less product. So that means that is the limiting reactant. And since this guy here, the water, has the possibility to produce more product than that lithium oxide can allow, that means that this guy is now considered our excess reagent. Okay? We'll run out of lithium oxide before we run out of water, is what this means. Okay? So, Li2O is the limiting reactant. That's the first answer of the problem that you need. Okay? If we want to determine now how much of the excess is remaining, we subtract these two values from each other. So we do our excess number of moles minus our limiting number of moles. So 4.44 moles of H2O minus 2.18 moles of H2O is equal to, there's 2.26 moles of H2O excess. So if we want to convert that now back into grams of H2O that's in excess, we could do a mole to gram conversion. So we say 2.26 moles of H2O. We do our mole to gram conversion, which again is our molar mass. So here the mole has to go on the bottom to cancel this out. So for every mole of H2O, we have 18.01528 grams of H2O. And that gives us an answer of 40.7 grams of H2O are in excess. So if we want to see how much of this water was used, we see we started off with 80 grams of our H2O that we started with. So if we want to see how much H2O was used, we say our 80 grams of H2O that we started with minus the amount that's left in excess. 40.7 grams of H2O is left in excess. So that means that we only used 39.3 grams of H2O that we actually used. So now we want to find how much of our product did we actually produce. So to do that, we take a look at our limiting reagent. So remember, the limiting reagent or limiting reactant, that determines how much of the product that we can actually produce. So we're going to use this 2.18 moles of H2O needed, and we can then convert that value into mass of our lithium hydroxide product. All right, so I'm going to erase all of this, and we're going to remember this 2.18 moles of H2O quantity that's listed right here. Okay, if we want to find our mass of product, 2.18 moles of H2O. And we want to convert this to moles of our lithium hydroxide product, which if we went back to our chemical equation, it would tell us that we had a 2-to-1 ratio. So for every 1 mole of H2O, we have 2 moles of lithium hydroxide. We can use our molar mass now to be able to convert from moles of lithium hydroxide into grams of lithium hydroxide. We need to put our moles of LiOH on the bottom to cancel out. We can see that we have 23.94634 grams of LiOH. And that gives us a final answer of 104 grams of LiOH. So this is a pretty complex problem with lots of different steps. And all those steps build upon themselves. Okay, so you can see how this would be a very attractive problem for me to be able to assign to you guys. Okay, lots of different steps, lots of different dimensional analysis and stoichiometry for you guys to be able to do. So you're going to want to practice these sort of problems quite a bit. Okay, so let's now proceed further from this now. The second part of the problem that I could then ask is if the reaction was only 92% efficient, if there's only a 92% yield, how much LiOH was actually formed? Okay, so if it only had a 92% yield, how much was actually formed? So remember, based on our limiting reagent calculations that we did, showing that we expected there to be 104 grams produced, that was our theoretical yield, the amount that we expect to get based on calculation. Here, we want to find out what is our experimental yield, how much did we actually produce. So we know the equation for percent yield. So percent yield is equal to our experimental over our theoretical times 100%. So remember, our experimental yield is the amount that we actually measure. The theoretical yield is the amount that we predict based on mathematics. Okay, so that theoretical, that's determined from our limiting reagent problem we just did. So in this problem, we're given the percent yield. We calculate the theoretical already, but we need to solve for the experimental. So what we first want to do is totally rearrange the equation so that we're solving now for our experimental yield. And so to do that, we'll rearrange the equation. And now it says that experimental is equal to our percent yield times the theoretical over 100%. Okay, we just rearrange the equation. So now we can just plug and chug. Our experimental yield is equal to 92%, which was given to us in the problem, times our theoretical yield, which we just solved in the last problem here, which was 104 grams of lithium hydroxide, over 100%. And so if we plug and chug here, we get 96 grams of lithium hydroxide was actually formed. So that would be our experimental yield that we determined. Okay, so this is the last slide. So acetylene gas, C2H2, is commonly used in high temperature torches. Write the chemical equation, including the phases of matter, for the reaction of acetylene with hydrogen gas to form ethane gas which is C2H6. How many grams of ethane can be produced from a mixture of 30.3 grams of acetylene and 4.14 grams of H2? Which is the limiting reagent? How much of the excess reagent remains after the reaction is completed? Okay, so this is a long problem. This is a sort of problem that you're going to be given on a test or a quiz. So you should be able to work this through. Okay, let's do it. So in this equation here, or in this problem, you actually were not given the chemical equation. So the first step would be to be able to actually write out the chemical equation that describes the experiment that we were talking about. So we have C2H2 gas plus H2 gas yields C2H6 gas. So hopefully you can see here that this equation is not balanced. There are only 4 hydrogens on the left, and there are 6 hydrogens on the right. So the way to balance this equation would be to put a 2 coefficient in front of the hydrogen gas. The next step would be to determine the molecular weights for each of the different components. So, trusting that you're able to do that, we'll say that the molecular weight for C2H2 is equal to 26.03808 grams per mole. H2 has a molecular weight of 2.01588 grams per mole. And C2H6 has a molecular weight of 30.06984 grams per mole. Okay, so if we start off and we have 30.3 grams of C2H2 to start off with. Measured quantity, that's always put over 1. We convert this to moles of C2H2 using our molar mass as our conversion factor. 26.03808 grams of C2H2 per mole. Now we're going to convert this to number of moles of H2. So we can both put both quantities into moles of the same thing, so we can then determine which one is limiting and which one is in excess. And so we see we have a 1 to 2 molar ratio here. So we can simply convert, saying that 1 mole of C2H2 is equal to 2 moles of H2 gas. If we plug and chug here, we get an answer that 2.33 moles of H2 gas are needed. So that's how many moles of H2 gas are needed to react with this 30.3 grams of C2H2. So now we need to do our starting amount of H2 gas, which is a 4.14 grams of H2 gas. Again, measured quantity over 1. And we use our molar mass here of H2, 2.01588 grams of H2 equals 1 mole of H2. And that says that there's 2.05 moles of H2 gas available. Okay, so we now have both of these quantities in moles of H2. So it's moles of the same thing. So now we're able to do an apples to apples comparison to see which one is excess and which one is limiting. So here we can see, since this 2.05 is smaller than 2.33, that means that H2 is limiting. So that's the first part of the problem, that H2 is limiting. see how much of the C2H2 remains, we subtract these molar amounts from each other. And you can see here that we go 2.33, our excess, that's in moles of H2, minus 2.05 moles of H2 that were used. That gives us 0.28 moles of H2 remain. Okay? This is not truly moles of H2, because remember, H2 is our limiting. This is the moles of H2 that we could make with the C2H2. So we're back calculating back to see how much of the C2H2 remains. So now we need to take that molar quantity and convert that back into grams of the C2H2 excess material. All right, so 0.28 moles of H2, which we had here, that's the amount excess remaining. Use our molar ratio to convert that back to moles of C2H2. So we have 2 moles versus 1. 2 moles of H2 for every 1 mole of C2H2. Okay, and then we can now convert moles of C2H2 into grams of C2H2 using our molecular weight. So that's this for C2H2. So that'll be 26.03808 grams of C2H2. Plug and chug, we get an answer of 3.65 grams of C2H2 remaining. Okay, the final step here is to determine how much of our product, the C2H6, that is formed. So to do that, we're now going to convert our number of moles of our limiting into our mass of product formed. So we start with our 2.05 moles of H2 over 1. We have a 2-to-1 molar ratio between H2 and C2H6. So for every 2 moles of H2, we have 1 mole of our product, C2H6. We can now use our molecular weight for C2H6 to be able to convert into grams of our product. For every mole of C2H6, we have 30.06984 grams of C2H6. Plug and chug, that gives us an answer of 30.8 grams of C2H6 formed. Okay, at this point, if I were to go on and tell you how much of the product was actually formed, we would then be able to determine the percent yield of this problem. All right, that's it for the material. Thank you for your time.